Pascal's triangle allows us to expand x plus y to the power n for any power of n. It provides the coefficients that we need. So for x plus y cubed, the numeric value of the coefficients is 1, 3, 3, 1. We can also name the coefficients. So for x plus y cubed, we call them 3c0, which is 1, 3c1, which is 3, 3c2, which is 3, 3c3, which is 1. And x plus y cubed expands to this if we use the numeric values for the coefficients, or this if we use the names for the coefficients. Now, we calculate the values in Pascal's triangle using the left-right addition process. 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, 1 plus 3 is 4, and so on. However, this is a very inefficient way to calculate the coefficients for large values of n. So, for example, if we wanted the 27th coefficient in the 129th row, which is called 128c27, it would be an awful lot of work to do so using that process. What we need is a process to calculate values of the coefficients in any row independently of other coefficients. So what we need is a formula that allows us to calculate NCR, a general coefficient, only using the numbers n and r. And it's worth being aware that both n and r start at 0. The first row is labelled with 0, since we wish to calculate x plus y to the power 0. The first coefficient in each row is labelled 0. So we have 0 in the first row, 0 as the first coefficient in the first row, and we can see the first coefficient in every row is labelled with 0. And of course, it is these numbers, which we are calling n, and these numbers at the bottom of the coefficients, which we are calling r. I'm going to start by presenting the formula for NCR, and the rest of the video, which is rather long, will discuss where it comes from. NCR equals n factorial over r factorial times n minus r factorial. And the definition for n factorial comes in two parts. If n is 0, then 0 factorial is defined to be 1. If n is an element of the set capital N, which is the set of counting numbers, the numbers 1, 2, 3, 4 up to infinity, then n factorial is the product of the integers from n down to 1. It is n times n minus 1 times n minus 2 ... times 3 times 2 times 1. Now, although I've given a formula for NCR and n factorial, in reality you rarely use them because the modern electronic calculator can compute them for you. Here I've shown a picture of a particular Casio calculator, and the factorial function is available above the x to the minus 1 button, which I've shown in this yellow box at the top, and here in expanded form we have x factorial above the x to the minus 1 button. And so to compute, say, 5 factorial, we use the key sequence 5 shift x to the minus 1, where the shift button is here at the top left in this yellow box. And your calculator will tell you when you press equals that 5 factorial equals 120. The NCR function is above the divide button. So in this yellow box at the bottom, which I've shown in expanded form here, we can see NCR written above the divide button. And so, for example, to calculate 12C7, we use the key sequence 12 shift divide 7 equals, and your calculator will tell you that 12C7 equals 792. Now, if you are only interested in how to compute factorials and NCR for given values of n and r, you know everything that you need to know and you can stop watching. On the other hand, if you are interested in seeing where the formula for NCR comes from, then please continue, but bear in mind that this is quite a long and complex video. I'm going to be considering the crab clause or FOIL expansion of expressions like x plus y cubed. And when we do such expansions, we usually lay out the brackets like this, horizontally. However, in this video, I'm often going to lay them out vertically, like this. So one particular term in the expansion may be generated by going x times y, and that generates x squared y, or in unsimplified form, xy. To generate the same term from the vertical layout of the brackets, we would go from x to x and then from x to y. And so we can see that this term, x squared y, corresponds to a particular route through those brackets where we choose either x or y at each bracket. To find a formula for NCR in terms of n and r, we need a better understanding of what happens when we expand the power of a binomial. So here I'm going to look at the expansions of x plus y squared and x plus y cubed. So if we look at the crab clause expansion of x plus y squared, we multiply x by x by y by x, and y by y. So we multiply each of two terms, x and y, by each of two terms, x and y coming firstly from the first bracket and secondly from the second bracket. And since we multiply two terms by two terms in every possible combination, we end up with 4 terms in the expansion. 1, 2, 3, 4. And we have every possible combination of multiplications of x and y. Now notice that for the third term, xy, I perhaps should have written that as yx, as I started with y and multiplied by x. But since yx equals xy, where x and y are real numbers, we can simply interchange the order of x and y. And so it ends up that the second term and the third term have precisely the same form, and we can therefore bring them together as like terms to produce 2xy when we simplify the expression. Now for the expansion of x plus y cubed, first note that x plus y cubed equals x plus y times x plus y squared. And we've seen that x plus y squared can be written unsimplified as xx plus xy plus xy plus yy. And so in this case, the crab clause expansion looks like this. We multiply each of two terms, x and y, by each of 4 terms, xx, xy, xy, yy. So we end up with 8 terms in the final expansion. And note that 2 times 2 equals 4 for the first expansion, and 2 times 4, which equals 2 times 2 times 2, equals 8 for the second expansion. We'll see why that is relevant in a moment. Now, of course, we have to simplify our expansion, and we have one term with 3 x's, which becomes 1x cubed. We have 1, 2, 3 terms with 2 x's and 1 y, which becomes 3x squared y. We have 1, 2, 3 terms with 1 x and 2 y's, which becomes 3xy squared, and we have one term with 3 y's, which becomes y cubed. And now we can see how the coefficients arise. We have a coefficient of 3 here because we have 3 terms with 2 x's and 1 y, and we have a coefficient of 3 here because we have 3 terms with 1 x and 2 y's. And if, for example, we were expanding x plus y to the 5, and we wanted to know the coefficient for the x cubed y squared term, we'd need to be able to find how many expressions contain 3 x's and 2 y's when we perform the expansion. Let's look at the expansion of x plus y cubed again, and let's see how we form terms containing x squared y. We get those terms whenever we have 2 x's and 1 y in the expansion. How many different ways can we produce terms like that with 2 x's and 1 y? To get such terms, we can choose x from the first bracket, multiply that with x from the second bracket, and then multiply that with y from the third bracket. Or we could choose x from the first bracket, multiply that with y from the second bracket, and multiply the result of that with x from the third bracket. Or we could choose y from the first bracket, multiply that with x from the second bracket, and multiply the result of that with x from the third bracket. There is no other way in which we could produce an x squared y term with 2 x's and 1 y. Now, the 3 in front of the x squared y term is called 3c1, and we can now see that 3c1 is counting the number of ways in which we can choose 2 x's and 1 y from 3 brackets, where each bracket contains x plus y. And the number 3 here is called 3c2, and that 3c2 is telling us the number of ways in which we can choose 1 x and 2 y's from the same 3 brackets. So let's review the expansion of x plus y cubed, which expands to these 8 color-coded expressions. The first point is that each term corresponds to a root through the brackets, and there are 8 roots in total, which corresponds to 2 times 2 times 2, and it's 2 times 2 times 2 because we have a choice of 2 at each bracket, either x or y. So, for example, our first root could be x to x, where we've chosen x at each bracket, and that corresponds to this term. Or we could go x to x and then x to y, which corresponds to this term. Or we could go x to y, y to x, which corresponds to this term, and so on. The second point is, at each bracket we have a choice of either x or y, and since we have 3 brackets, we select either x or y 3 times, which means that each term in the final expansion has 3 of either x or y, no more and no less. And the third point, we choose either y or not y at each bracket, and since there are 3 brackets, we do that 3 times, which gives us terms like xxx if we don't choose y at any bracket, xxy if we choose y at 1 bracket, xyy if we choose y at 2 brackets, and so on. And so if we're interested in the term that looks like 3c1 x squared y to the 1, the 3c1 tells us how many ways that we can choose 2 x's and 1 y by making those choices as we go through the brackets. And this notation, 3c1, is generally read as 3 choose 1. Now in the general case, we're expanding x plus y to the power n, where n is some arbitrary positive integer. And the general term looks like ncr times x to the n minus r times y to the r. And the ncr, which will be read n choose r, is the number of ways to choose r y's from n brackets. And it is this quantity, ncr, for which we require a formula in terms of n and r. Here I'm considering the expansion of x plus y to the 4, and I've shown the 6 choices that make up the term 4c2 x squared y squared, i.e. I'm claiming that 4c2 equals 6. To contribute to the 4c2 x squared y squared term, we have to choose terms that contain exactly 2 y's, and we can do that as follows: y at the first bracket, y at the second, y at the first, y at the third, y at the first, y at the fourth, y at the second, y at the third, y at the second, y at the fourth, y at the third, y at the fourth. And there are no other possible choices that contain exactly 2 y's. If I don't choose a y, then I must choose an x, and so I can fill in the rest of this diagram as follows. And we can see that each term in those 6 choices contains exactly 2 y's and 2 x's as required to be in the 4c2 x squared y squared term. And if we consider, say, this term, the third, illustrated as a root through the brackets, it looks like this. We choose y, then x, then we choose x after x, and finally we choose y after x. And each of those 6 terms can similarly be illustrated as a root through those 4 brackets. Now, of course, we still need the formula for NCR. I'm simply going to present it without proof here, as the derivation is somewhat time-consuming. NCR equals n factorial over r factorial times n minus r factorial. And the definition for n factorial comes in 2 parts. If n is an integer in the set capital N, the set of counting numbers, i.e. 1, 2, 3, 4, 5, up to infinity, then n factorial is the product of the integers from n down to 1. N times n minus 1 times n minus 2, all the way down to times 3 times 2 times 1. If n equals 0, then n factorial is defined to be 1, and we shall see why that is the case later. So, for example, 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1. And note that 4 times 3 times 2 times 1 is 4 factorial. So 5 factorial is in fact 5 times 4 factorial, which is 120. And does n factorial have any meaning, you may ask? Well, yes it does. N factorial gives the number of different arrangements of n distinct objects. And here we can see a simple example. If we have the 3 distinct letters A, B, C, we can arrange them in 3 factorial, which is 6 different ways. ABC, ACB, BAC, BCA, CAB, CBA. So here are a couple of examples. 3c2 from the definition becomes 3 factorial over 2 factorial times 3 minus 2 factorial. That turns into 3 factorial over 2 factorial times 1 factorial. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. 1 factorial is 1. And that simplifies to 3. And 3c2 occurs in the expansion of x plus y to the 3, and it is the entry where r equals 2, which is this value, 3. So our calculation is correct. From the definition, 6c3 is 6 factorial over 3 factorial times 6 minus 3 factorial, which becomes 6 factorial over 3 factorial times 3 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 3 factorial is 3 times 2 times 1, and that simplifies after a little arithmetic to 20. And 6c3 occurs in the expansion of x plus y to the 6, and I've given both the numeric and the named values on the left hand side here, and we can see that 6c3 is this entry. Numerically it's 20, as we have shown from the definition. Now let's look at 6c0. From the definition, that becomes 6 factorial over 0 factorial times 6 minus 0 factorial. That turns into 6 factorial over 0 factorial times 6 factorial. The 6 factorials cancel to give us 1 over 0 factorial. But we now have a problem. What is 0 factorial? N factorial is only defined for n in the set n, capital N, which are the numbers 1, 2, 3, 4, 5 up to infinity, and the definition is this. That does not work for 0. However, we know that 6c0 equals 1 from this table here, 6c0, 1. So we can say that 6c0, which we've calculated to be 1 over 0 factorial, equals 1, and we can solve this equation to show that if 6c0 must be 1, then 0 factorial must be 1 over 1, which equals 1. So we must in fact define 0 factorial to be 1 in order to make the formula for NCR work correctly when r equals 0. And it's worth being aware that 0 factorial equals 1 does not come from this formula. We simply have to define that to be the case in order to make the formula for NCR work correctly. Now, we can describe NCR as giving the number of different ways of choosing R objects from a collection of n distinct objects where the order of selection is irrelevant. And so, for example, here we have 5 distinct letters, A, B, C, D, E, and if we calculate 5C2, we will find that it is 10. And I have shown here the 10 possible choices of 2 of those letters from the 5 when we are not interested in the order. So, for example, AB is considered to be the same as BA. NCR is generally read as N choose R, and it can also be denoted by this mathematical expression, 2 brackets with N at the top and R at the bottom. Both the notations NCR and this bracket notation are commonly used in mathematics.